Mechanisms and Catalysts, Lecture 18. So we're going to complete this sort of discussion of kinetics by looking at how a stepwise method of determining how these reactions proceed from reactants to products, which we're going to call mechanisms, and then see how this effect of a catalyst, or how a catalyst affects these rates. But first, let's go back and talk about some underlying theory about how the process it takes to go from reactants to products. What has to happen? And there's a couple of theories we're going to talk about or rediscuss. The first is this collision theory and concentration. So we said that in order for a reaction to occur, the two reactants, or the reactants, had to collide with each other. So that is true. If in order for a reaction to occur, they have to come in contact. Two reactants or a single reactant has to come in contact for that reaction to occur. And increasing the concentration is going to then increase the number of particles per unit space, which is going to increase the likelihood of a collision. Right? Increase the number of collisions, increase the speed that this reaction occurs, or the reaction rate. And the number of collisions is going to be related to the product, the amount of each one multiplied together, not their sum. So it's not which is why in the rate law, we're multiplying those two reactants together, right? Not adding them, because the concentrations are multiplied together to get this collisions. And we saw that there's an effect of temperature, that we have increase in temperature is going to increase the rate of reaction. Because the kinetic energy is going to occur, or increase, which means that we're going to get molecules moving faster, which means they're more likely to come in contact with each other, or per some given unit time. And in fact, for many reactions, an increase in 10 degrees Celsius is going to double or triple the rate of the reaction as it occurs, right? For many reactions. So then we can relate this rate constant K as a function of temperature, right? So since the concentrations aren't related to temperature, the only thing that's going to affect the rate law is this proportionality constant, or this rate constant. And we see that the Arrhenius equation relates this rate constant K to this temperature, where the rate constant K is equal to A, which is a frequency factor, how frequently those reactions are occurring and are successful, times e to the negative EA. EA is the activation energy, which we'll talk about here in a second, divided by RT, where R is this, again, our gas constant, or this 8.314. So the higher the temperature, the higher we're going to get this rate constant is going to be, which is going to give us a larger rate. So we introduced this idea of this activation energy. So in order to be effective, or the reaction to occur, these collisions must exceed some amount of threshold energy. Right? This is what we refer to as the activation energy. Right? There's some hump in energy that we have to overcome, that these collisions have to overcome to get the molecule into an excited state, or activated state, which we're calling the activation energy. Right? So it's a hump in our energy diagram, if you will. The lower the activation energy, the lower this hump, the faster the reaction is going to occur. Right? The less energy overall is needed for the reaction to move from reactants to product. So the lower the activation energy, the larger this frequency is going to occur, this F, the faster the reaction, the collisions are going to be successful, which means we have a larger rate constant, which means we have an increased rate. So we relate this back to the temperature, so tie these two things together. Increase the energy, we're increasing the kinetic energy, as we said, which means that we're having more frequent collisions. And at this higher temperature, the collisions that do occur are going to be more likely to be of sufficient energy to overcome this activation energy. Right? So we can relate those two things together. We can calculate this activation energy using modifying this Arrhenius equation. Right? So we take the Arrhenius equation at the rate constant at two different temperatures. We can then calculate, again, a straight line form of this Arrhenius equation. So if we have data from two different temperatures, then the natural log of the rate constant at the second conditions divided by the rate constant at the first conditions is equal to a negative activation energy over R times 1 over the temperature of the second set of conditions minus 1 over the temperature under the first set of conditions. Right? So, and then you'll do this in lab where you'll relate the rate, or you'll calculate the activation energy by looking at these rate constants at two different temperatures. Get 2 points on this line. The slope between those is going to be a negative activation energy over R. Again, we find a lot in these kinetic equations that graphing things will help simplify our math. So we know that these reactions have to come in contact. They have to collide, and they have to collide with sufficient energy for the reactions to occur. Right? The other thing that's important is the actual molecular structure. They have to collide in the correct arrangement. Right? So now we have three things that must be true in order for a reactant to move to product. They have to collide. Right? They have to collide with sufficient energy, and now they have to collide with the correct relative orientation. They have to collide in such a way that it's favorable for that interaction to occur. Right? And the probability that this this collision is going to be in the correct orientation is this term A from the Arrhenius equation. Right? It's A is equal to P times the Z, where P is the orientation probability, the probability that those two are coming together under the correct orientation, and Z is the collision frequency, how frequently those are occurring. So this A, this proportionality constant, really gives us an indication of how likely an individual collision is going to be successful. And we see that this P, this proportionality probability factor, is going to be determined by how structurally complex those reactants are. If we have a fairly simple structure, we would get a fairly large p-value. The more a large number of collisions are going to be successful. If we have a very complex reaction or structure where they have to come together in a very specific way, our probability factor is going to be small. Right? Again, the easiest way to calculate, well, these A's are typically calculated experimentally. Right? So we're going to monitor all these values under a variety of conditions and determine this A value. We can theoretically achieve it using modeling software, but most of the time it's experimental, like all things kinetic. So this collision theory relies on what we call this transition state theory. That once we get a successful collision, we are going to move from those reactants into a transition state, something that is unstable, but is in the correct orientation where we can then descend into a lower energy of our reactants. So either they can unsuccessfully and go back to the reactants, or successfully combine and go. So in this transition state, we have an unstable set of bonds that can lead to the products that we are desiring. And this transition state is going to exist at the top of our activation energy hump. Right? So if we think about the energies, we have reactants down here, the activation energy is up here. The transition state is going to exist at the top of this energy. So higher energy is going to be less stable, but it can occur. And then you can have one of two possibilities of where it's going to go, back to the original reactants or to the products. in both of these cases, we're looking at a step-by-step reaction to occur. So we can define the steps that must be taken to move from reactants to products, and that's what we refer to as a mechanism. The overall process of the chemical reaction can be separated on a molecular level to a series of what we call elementary steps or elementary reactions. So these elementary steps are an atomic view of what things need to happen to move us from reactants to products. All right, so if we look at a reaction of 2NO gas plus O2 gas goes to 2NO2 gas, we see that in the overall reaction, we don't, that N2O2 isn't anywhere in this overall reaction. But if we monitor the reaction as it's proceeding, we can detect a compound N2O2, right? Which means that it's somewhere in the steps it takes to go from NO and O2, N2O2 must be formed. So then we can propose this mechanism where the two NOs come together to form N2O2, and then that N2O2 is reacting with an oxygen molecule to give us this 2NO2. So these elementary steps, the reaction mechanism, must give us the overall reaction. And it can involve what we call intermediates. Intermediates are species that appear in a reaction mechanism, but not in the overall balanced equation. The definition, or one definition of an intermediate, is something that's formed in an early elementary step and then consumed in a later elementary step. So we can see here our intermediate is N2O2. And in these mechanisms, in these elementary steps, because we're talking about single atoms reacting in a stepwise arrangement, here, these elementary steps can be directly related to the rate law through this molecularity idea. So the molecularity of the reaction is the number of molecules reacting in each elementary step. So if there's one molecule reacting, we call that a unimolecular reaction. If there's two, it's a bimolecular, three, termolecular, and so on. And we see that these, for the elementary steps, and the elementary steps only, the molecularity of that reaction is going to be related to the order within the rate law. So if we see that the rate determining step has A going to products, molecularity of 1, then the rate law can be described as the rate is equal to K times A to the first. Right? If it's A plus B, then the rate law then would be rate is equal to K times concentration of A times the concentration of B. If it's A reacting with another A, then the rate is going to be equal to the rate constant K times A squared. So the rules for writing these mechanisms is that the sum of the elementary steps must equal their overall reaction. And the rate limiting step, the slow step, has to predict the overall rate law for that reaction. Right? So if the rate determining the slow step is the very first step, then that one must be able to give us the overall reaction. If it's not the first step, if it's some other one, then through substitutions, that overall reaction, the rate law with respect to our initial reactants, has to be determined by that step. And this rate determining step, as I said, is the slowest step. So it's the one that's going to really dictate the speed at which we move from reactants to products. So then if we think about these catalysts, what a catalyst is doing is changing the mechanism which the reaction occurs. So it's changing the steps it's taking to go from reactants to products. And what it's doing is essentially lowering the activation energy. Right? So if we add a catalyst, we're lowering the activation energy because we're changing the mechanism. We're changing the path that the molecules take to go from reactants to products. But it does so by lowering the activation energy, which is going to increase the speed of our overall reaction.